Our objectives tonight are to determine whether a random variable is binomial, and there's 4 conditions we're going to check to see if it is binomial. Determine the probability distribution of a binomial random variable, compute binomial probabilities, and also compute the mean and the variance of a binomial random variable. Objective 1 is to determine whether a random variable is binomial. And we're going to explain this by using this little scenario here. Suppose that your favorite fast food chain is giving away a coupon with every purchase of a meal. 20% of the coupons entitle you to a free hamburger, and the rest of them say, "Better luck next time." 10 of you order lunch at this restaurant. What is the probability that 3 of you win a free hamburger? In general, if we let x be the number of people out of 10 that win a free hamburger, what is the probability distribution of x? In this section, we'll learn that x has a distribution that's called a binomial distribution, which is one of the most useful probability distributions. For binomial distributions, we need to have a fixed number of trials. N we use as the variable to represent our number of trials. In this scenario here, what would N be equal to? 10. 10 of you go to the restaurant and order a burger and get a coupon. P is the probability of success. If we're calling a success getting a coupon for the free burger, what's the probability that that would happen? How would we express that 20% as a probability? 0.2. And then x here is the number of successes. And for this particular problem, we were asked what's the probability that we get exactly 3 successes. Now I told you that this is a binomial distribution, or this scenario represents a binomial distribution, because the following conditions are satisfied. A random variable that represents the number of successes in a series of trials has a probability distribution called the binomial distribution. The conditions are that you must have a fixed number of trials. We did for that problem. It was n equals 10. There are 2 possible outcomes. We call those outcomes success and failure. Now, don't let the positive connotation of the word success and the negative connotation of the word failure fool you. If you're studying the number of deaths due to nosocomial infections in a hospital, a death would be considered a success. Death we don't usually think of as a success, but in that situation it would be. Also, the probability of success has to be the same for every trial. In the previous example with the burgers, we were told that 20% of the coupons awarded a free burger, so the probability of getting one of those coupons was 20%, or 0.2, for everybody. It didn't change. The probability of success has to be the same for every trial. Also, the trials have to be independent of each other. This means that the outcome of one trial does not affect the outcomes of the other trials. Just because you got a free burger, does that mean that the person behind you is not going to get a free burger or is going to get a free burger? No, your chances are equal all the time. Those would be independent. The random variable x represents the number of successes that occur in your binomial distribution. So for the notation, n is the number of trials and a lowercase p is the probability of success. For this example, we want to see which of these 3 conditions satisfy the conditions of a binomial experiment. Let me write down the 4 conditions that must be satisfied for a binomial experiment just to keep that fresh in our mind. In order to have a binomial distribution, these 4 conditions must be satisfied. You have to have a fixed number of trials. You can only have 2 outcomes, which we categorized as success and failure. Your trials have to be independent of each other. And then P, the probability of success, has to be the same for all trials. This upside down capital A is a quantifier that we use to mean for all or for every. You'll see me use that quantifier to save on handwriting as we go through and take notes throughout the remainder of the semester. Looking at this first scenario, we're told that a fair coin is tossed 10 times. Let x be the number of times that the coin lands on heads. Is this a binomial experiment? You want to say yes. Okay, why do you say yes? If it is yes, then we have to be able to identify all 4 of these things. Right, all 4 of these conditions are met, so therefore yes, this is binomial. 5 basketball players each attempt a free throw. Let x be the number of free throws that are made. Let's go through the process here. Do we have a fixed number of trials? Everybody gets 1 shot. N equals 5. Do we have only 2 outcomes? We'll say basket or miss. Are our trials independent of each other? Is the probability of making a basket the same for each person? Some people shoot better than others, so P is not the same for every person. The probability of making the basket is not the same. If you have a kid from the chess club shooting against an NBA pro, is the probability of them making the basket the same? No. This is not binomial because it fails number 4. It fails condition 4. 10 cards are in a box. 5 are red and 5 are green. 3 of the cards are drawn at random. Let X be the number of red cards drawn. Does this represent a binomial distribution? Do we have a fixed number of trials? N is 3. Do we have only 2 outcomes? Red and green. Do we have independent trials? No, we don't, because once I draw 1 card out of that box, it changes the probability of the next card. So this is not a binomial because it fails number 3 and 4. It fails 4 because it fails 3. I'm just going to put it fails 3. Objective 2 is to determine the probability distribution of a binomial random variable. Let's look at the binomial probability distribution. Consider the binomial experiment of tossing 3 times a biased coin that has a probability of 0.6 of coming up heads. The probability of coming up heads is 0.6. What is the probability of coming up tails? 1 minus p is equal to 0.4. When you're tossing a biased coin 3 times, you have several different ways that you can come up with getting exactly 2 heads. X here represents the number of heads that come up. If we want to compute P of 2, the probability of 2, that's the probability of getting exactly 2 heads out of the 3 coin tosses. Now there's several different ways that we could get exactly 2 heads out of 3 coin tosses. I could get head, head, tail. I could get head, tail, head. I could get tail, head, head. Would you agree with that? This is the 3 different combinations of heads and tails that I could get. The probability of getting this would be, remember our coin tosses are independent of each other, right? Are our coin tosses independent of each other? If I toss a coin 1 time, does it affect what happens the next time? It's a biased coin. That just means that the probability is not going to be 50-50. If it's an unbiased coin, then you have a 50% chance of getting a head and a 50% chance of getting a tail. If it's a biased coin, this means that it's biased towards head. You're more likely to get a head than you are to get a tail. If I wanted to calculate the probability of head, head, tail, that would be equal to 0.6 times 0.6 times 0.4, because the probability that I get a tail is 0.4. That's one way that I could get 2 heads. This is another way that I could get 2 heads, and that would be 0.6 times 0.4 times 0.6. And this would be another way, the last way that I could come up with 2 heads and a tail. And that would be 0.4 times 0.6 times 0.6. Now if I looked at each one of these individually, knowing that multiplication commutes, I could say that this is 0.6 to the second power times 0.4 to the first. This is also 0.6 to the second power because I have 2 0.6's right here that I'm multiplying times a 0.4 to the first. And this is also a 0.6 to the second times a 0.4. Does that make sense? How I came up with each of these individual probabilities? I'm taking you through the process here that's mentioned in this long wordy paragraph. If I want to let X be equal to exactly 2 successes, this is the way that I could do it, like this, or like this, or like this. When I say the word or between probabilities, what do we have to do to the probabilities? I've got to add them together. So when I add these together, well, these are all 3 the same, so I've got 1, 2, 3 of them. That's going to give me 3 times the probability of success raised to the second times the probability of failure, which is 0.4. To generalize what just happened here, order doesn't matter with these probabilities. So this 3 actually ends up being 3 choose 2 times 0.6 raised to the 2 times 0.4 raised to the 3 minus 2. In general, the rule is this. It's n choose x, where n is the number of trials that you have, x is the number of successes, times p, the probability of success raised to the x, times 1 minus p raised to the n minus x. This is the formula for calculating the probability for the binomial random variable x, if you're calculating it by hand. Fortunately for us, we don't have to calculate these by hand because this formula is already pre-programmed into your calculator. And I'm going to show you how to use your calculator to find these probabilities. The first problem, I'll use this formula just to show you that when I use the formula that's programmed in the calculator, we get the same thing. Objective 3 is actually computing the probabilities, and I am going to need more room here because I am going to show you how to use your calculators. For this problem, we're told that the Pew Research Center reports in June 2013 that approximately 30% of U.S. adults own a tablet computer such as an iPad, a Samsung Galaxy Tab, or a Kindle Fire. Suppose a simple random sample of 15 people is taken. Use the binomial probability distribution to find the following probabilities. Remember, the formula is this: p of x equals n choose x times p to the x times 1 minus p to the n minus x. So our first step would be to identify what these variables are. Remember, x represents the number of successes. So we want to find the probability that exactly 4 of the sampled people own a tablet. So what is x going to be here? 4. If we're calling a success owning a tablet, and we're asked to find the probability that exactly 4 of the sample people own a tablet, x is 4. What is n equal to? That's located up here. N is 15. What is p equal to? 0.3. We were told that 30% of the people own a tablet computer. X we're calling a success, which is owning a tablet computer. Dropping in these numbers into the formula, we end up with the probability of exactly 4 successes is 15 choose 4 times 0.3 raised to the 4th times 1 minus 0.3 raised to the 15 minus 4. I could clean this up. So that's 15 choose 4 times 0.3 raised to the 4th times 1 minus 0.3 is 0.7 raised to the 11th. Now let's get out our calculators. So we need to do 15 choose, and how do I get to the combination? Math, probability, number 3. 15 choose how many? 4. Times, so I need to move my arrow over so that this is not down as a subscript with the 4, times 0.3 raised to what power? The 4th power, times 0.7 raised to the 11th. If your times 0.7 is up here in the exponent with the 4, you've got to remember to hit the arrow to the right to drop your cursor back down into the line where you want to type in your information. So we do this and we end up with 0.2186. Now I told you there's an easier way to do this on your calculator, and I'm going to write down the steps for you for how to do this on your calculator using the binomial PDF. The first thing you want to do is you want to hit second bars, and if you have a newer calculator you want to go up to letter A, the binomial PDF, and hit enter. If you have the older operating system, you're going to go up to 0, I believe it is, and it says binomial PDF, and hit enter. Everything else stays the same. And once you hit enter, it's going to pop this onto your home screen, and then you're going to need to put in numbers for n, comma, p, comma, and x, and then hit enter. But it's going to put this on your home screen. You have to type in what's in blue. For everybody else, our calculator is going to take us to a screen that prompts us what numbers to put in. So then we're going to put in the numbers for the trial, for the p, and for the x, the number of successes. Doing this problem that we just did using the binomial distribution, we're going to hit second bars, go up to letter A for the newer operating system, hit binomial PDF. The number of trials we said was 15. The probability of success was 0.3, and the number of successes we said was 4. Then you go down to paste and hit enter, and notice you get the exact same thing. So you're welcome to use this formula for the binomial distribution, the PDF, or you can use your calculator, the one that's pre-programmed in. Your call. I don't mind, use either one, but notice you get the same answers. After you scroll down to paste, you had to hit enter twice to get the answer. Part B says to find the probability that fewer than 3 of the people own a tablet or computer. Fewer than 3. X would be equal to what? Fewer than 3 is 4 fewer than 3? No. 1, 2, that's it? So 0. Remember, X is the number of successes. You could have 0 successes. So for this problem, I would use the binomial PDF to say that I'm looking for the probability of 0 plus the probability of 1 plus the probability of 2, and that's it. And I could expand this out by hand using the binomial PDF, where n is 15, p is 0.3, x is 0, plus the binomial PDF for n equals 15, p equals 0.3, and x equals 1, plus the binomial PDF for n equals 15, p equals 0.3, and x equals 2. And how would I put that in the calculator? I'm glad you asked. You just put it all in. So I'm going to clear this out and we're going to look at this problem. So we hit second vars, go up to letter A to get to the binomial PDF. We have 15.3 and 0. We hit paste, only now we don't hit enter, we hit plus. And then second vars, binomial PDF. N is 15, p is 0.3, x is 1. We hit paste. We don't hit enter yet, we hit plus. We got to do this again for 2. So second vars, go up to letter A, and we change that x value to 2, hit paste, and now we hit enter because I've got 3 of these in there with the x changing from 0 to 1 to 2. So now if I want to see it all, I can see that I've got the binomial PDF where x is equal to 2, 1, and 0, and the n's and the p's are the same for all of those. Now when I hit enter, it gives me a probability. What I want to show you is I could get the same answer using something that's not the binomial PDF, but really, really close to it. Second vars. Look at this. Do you see right below the binomial PDF, it has something called the binomial CDF? The binomial PDF is what you use if you want a particular value of x, like x equals 4, x equals 2, x equals 1. The binomial CDF is what you use for a cumulative value of x from 0 to x. Here I want the cumulative probability from 0 to 2. So instead of using the binomial PDF, I could have done the binomial CDF, where n is equal to 15, p is equal to 0.3, but x now is equal to 2 because I want to accumulate from 0, 1, and 2. The CDF accumulates, the PDF is for a particular value. So now we go to our calculators, and I'm going to select the binomial CDF. My number of trials is still 15, my probability of success is still 0.3, and my x value now is 2 because I want to go from 0, 1, and 2. And I paste this on my calculator, and guess what? I get the exact same answer as adding up all those individual PDFs. It's a time saver. The kicker is you have to be starting at 0. The CDF starts at 0 and goes up to whatever number you type in for x. Up to and including whatever number you type in for x. This one's with the PDF and you had to add 3 of them together. This one's with the CDF and you only have to do it once. Part C. Find the probability that more than one person owns a tablet or a computer. Now our event is more than one person. So if I have 15 people, it's possible to have 0 of them own a tablet, 1 of them own a tablet, 2, 3, 4, all the way up to 15. If my event is more than 1, then this would be my event, wouldn't it? More than 1. Because more than 1 starts with 2, doesn't it? We don't include the 1 because 1's not more than 1, but 2 is more than 1, and 3 is more than 1. All of these numbers here are more than 1. That's our event. What would we call this region right here with the 0 and the 1 in it? It's the complement of the event. We said that the complement is whatever is in your sample space. Your sample space is all the numbers from 0 to 15. It's whatever's in your sample space that's not in your event. So this would be the complement. How can I use the complement to find the probability of the event? Because if I did this head on, I would have to find the binomial PDF of 2 plus the binomial PDF of 3 plus the binomial PDF of 4. And that's going to be a pain. It's not impossible, but it's very, very tedious. So how could I find the complement to help me? Because to get the probability of 0 and 1, all I got to do is the binomial CDF for 1. Right, so the probability of our event is equal to 1 minus the probability of the complement of the event. And the probability of this complement, if we use the same technique we did in part B with the CDF, I could say that this is going to be 1 minus the binomial CDF, where n is equal to 15, p is equal to 0.3, and what is x going to be equal to? 1. Because 1 is the highest number that I've got in my complement. And remember, the CDF includes the probability of whatever number you put here. So this would be the probability of 0 plus the probability of 1. So on my calculator, this would look like the following. 1 minus second vars, go up to the binomial CDF, n is 15, p is 0.3, and x is now 1. And so I'm finding the probability of the event using the probability of the complement, and that's what we get. This is 1 minus the probability of the complement. The complement here just included the 0 and the 1. And we get 0.9647. Do you remember using the complement to find probabilities before? Do you see how what I've listed here in red is all of the number of successes that are possible if I have 15 trials? I could have no successes, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 15. More than 1 means I'm looking at 2 to 15. That's the event that I'm interested in. The complement would be everything that's not from 2 to 15. That's just these two. The probability of the event is 1 minus the probability of the complement. That CDF is how we find the probability of the complement, because remember, CDF start at 0 and go all the way up, adding probabilities as you go, up to whatever number you put here. Is this the only way I could have solved this problem? No, I could have added all of these up individually using the binomial PDF. Or I could have done the CDF for all 15 and then subtract off the probability of 0 and the probability of 1. There's a whole bunch of different ways I could do it. The CDF for 15 actually is 1 because that's everything, isn't it? If you use the PDF here, you get a 9.4 instead of a 9.6. You use the CDF if you're accumulating values. Here I'm accumulating, meaning I'm looking at p of 0 plus p of 1. I'm accumulating. I'm adding the probabilities as I go. Up here we used a CDF because I wanted to accumulate the probabilities from 0, 1, and 2. So I added the probability of 0 to the probability of 1 to the probability of 2. If I did them individually, I would use the PDF because I only have one number for x. When I use the CDF, I put in the maximum value and it adds up the probabilities from 0 to, in this problem, it was 2. So it's 0, 1, 2. The CDF accumulates. It's a cumulative probability. Let the alliteration help you. P for a particular value of x, that's just one value of x. C for a cumulative value of x, and that means from 0 all the way up to whatever x is equal to. Good question. I'm glad you asked for clarification. And that's our answer for part C. Let's look at part D now. Part D asks us to find the probability that the number of people who own a tablet computer is between 1 and 4. So here x is equal to 1, 2, 3, 4. It's almost the CDF, it's just not including what? The 0. So guess what I can do? I can do my binomial CDF with 4 and then subtract off the binomial PDF for 0. Now let's talk about why this works that way. The binomial CDF is the probability of 0 plus the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4. This whole thing right there is the binomial CDF. And then I subtract from it the binomial PDF for 0, and that's just the probability of 0. So if I have all of this and I subtract P of 0, guess what I'm left with? These are going to cancel out, and I'm just left with what I wanted. 1, 2, 3, and 4. X equals 1, 2, 3, and 4. Do you see that what I have written out here is just this part right here? Probability of 1 plus probability of 2 plus probability of 3 plus probability of 4. This is the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4. So if we put this in our calculator, we get 0.5017. And you're going to hit second vars, go up to binomial PDF for each one of these. But instead of hitting enter to get the value on the home screen, you hit plus. You hit that plus right there. Now I'm going to show you and write up the other way to do it with the CDF. With the CDF, I could do the binomial CDF 15.34 minus the binomial PDF 15.3 and 0. What that CDF does is it finds the probability of 0 plus 1 plus 2 plus 3 plus 4. And then it subtracts from it the probability of 0, which is what I have up here. So let's go through and do this on our calculator. I'm just going to do the second one, the binomial CDF, 15.3 and 4, minus the binomial PDF with 15.3 and 0. And we get the 0.5107 that you got before. Objective 3 is finding these probabilities by using tables, and this is probably the easiest way to do it. So using the same information we've been using, where n is equal to 15, the probability of having a tablet is 0.3. We've got this table from the appendix of your book, and it says n is equal to 15, x is your number of successes, and then going across the top of this table we have values for p. For our problem, we're going to be using this column of the table because we said our probability of success is 0.3. For part A of this problem, we're asked to find the probability that exactly 5 of the sample people own a tablet. So that's where x is equal to 5, and that's going to be looking at the table where these two things intersect, and that is 0.206. Part B says find the probability that fewer than 4 people own a tablet. Fewer than 4 is this right here from 0 to 3. So that means that I add these three numbers up. And that's going to give us 0.005 plus 0.031 plus 0.092 plus 0.170. And we add that together and we get 0.298. Part C is to find the probability that the number of people who own a tablet is between 6 and 8. I'm still looking at this column right here. Between 6 and 8 is going to be these, 6, 7, and 8. So I go over to my table and I add up these three numbers. This would be 0.147 plus 0.081 plus 0.035, and when I add those numbers together, what do I get? Objective 3 is finding probabilities using the binomial probabilities on the TI-84 graphing calculator. I said we use the PDF if you want a particular value, for example, x equals 3. We use the binomial CDF for a cumulative value. So for example, if x was equal to, let's say, less than 4, then x would be equal to 0, 1, 2, and 3, and that would be the binomial CDF where x was equal to 3. And you would need to put in numbers for n and p depending on what the problem is. So we're not going to take the time to rework the problems that we just did. Here's the definition once again of the binomial PDF and the binomial CDF and how to access them on your calculator. Remember, if you have the older operating system, you will just see the binomial PDF on your calculator home screen. You've got to type in numbers for n, p, and x in that order. You need to make a note on your formula sheet that you need to put in n, comma, p, comma, x using your calculator. You got to manually enter those. Everybody else, our calculator prompts us with what to put in. Objective 4 is to compute the mean and the variance of a binomial random variable. Once you've verified that you do have a binomial distribution, the mean is going to be equal to n times p, where n is the number of trials, p is the probability of success. The variance is n times p times q, where q is 1 minus p. Q is the probability of failure. If you don't like that, you can write it like this, 1 minus p. I'm just trying to get less writing in here. And then the standard deviation is always equal to the square root of the variance, and that's the square root of npq. These definitely need to be on your formula sheet for chapter 6. So here's an example problem. We're told the probability that a new car of a certain model will require repairs during the warranty period is 0.15. A particular dealership sells 25 such cars. Let x be the number that will require repairs during the warranty period. Find the mean and the standard deviation of x. We need to first identify what n is equal to. What is n? What is p? We're calling a success needing a repair, 0.15. And for this problem, we're looking for x. What is q? Because I am going to need that for the standard deviation. What is q? If p is 0.15, q is 1 minus 0.15, and that is 0.85. So for this problem, the mean is n times p. What is n times p? That's 25 times 0.15. And what is 25 times 0.15? 3.75. Next is the standard deviation. And the standard deviation, we're told, is the square root of npq. So that's going to be the square root of 25 times 0.15 times 0.85. 0.85 is the probability of failure. So we go to our calculator and we hit the square root, second square root, of n times p times q, enter, and we get the standard deviation is 1.785. Mean, variance, and standard deviation are just formulas that depend on the values of n, p, and q. Put that on your formula sheet.